All right, so we ended off with this person rappelling down the cliff. Okay? It's a work energy theorem question, which means that their energy at the bottom of the cliff is not equal to their energy at the top of the cliff. Okay? If that is the situation, if your energy, mechanical energy at the bottom of the cliff and the top of the cliff are equal, you are dead. Because all of your potential energy from the top of the cliff will have been converted into kinetic energy at the bottom of the cliff, which will allow you to do work on the ground. In other words, making a little person-shaped hole in the ground at the bottom of the cliff, and that would be undesirable. That's why you rappel. It's why you use a rope. Anyone ever rappelled before? It's fun. Okay? But what's one thing you have to be careful of besides not falling? That's the obvious thing. When you are rappelling, your rope goes through a carabiner. All you do is change the angle of the rope to allow it to slide through this metal loop. Okay, that's what a carabiner is essentially. Okay, so as you're rappelling down, the rope is sliding through the carabiner. What is there a lot of? Friction. Okay, one thing you have to be careful of when rappelling is that you do not touch the carabiner, because it will be what? Raging hot. Okay, you will burn your forearm on it if you touch it if you've been rappelling for a while. It will get really, really hot because of all the friction. What is all that friction doing? It's slowing you down. It's making sure that you don't have the same amount of energy at the bottom of the cliff as you had at the top. That way you'll be going much slower than you would if you just fell. Okay, so that's what we're looking at here. Okay, we have work still equaling a change in mechanical energy. Okay, that doesn't change. Okay, in any case, there's always going to be work being a change in mechanical energy. All right, the two places we're comparing are the top of the cliff and the bottom of the cliff. So just like yesterday, that's going to mean our final mechanical energy minus our initial mechanical energy. Okay, so that will be our final potential energy plus our final kinetic energy minus our initial potential energy plus our initial kinetic energy. Okay. Are any of those four forms of energy zero? Which ones? Okay, which one in the second? Yeah, this one here. Sorry. This is initial. Sorry. Ki, Eki is zero. Why is the initial kinetic energy zero? Yeah, I'm just standing at the top of the cliff initially. I'm not moving. I'm just standing there. I only have potential energy when I'm standing at the top of the cliff. So my initial kinetic energy is zero. And there's one other one that's zero. What is it? Right, your final potential energy, because when you're at the bottom of the cliff, you can't fall anymore. So you don't have any potential energy at the bottom. So this breaks down to a pretty simple calculation. I'm just taking my final kinetic energy, which is my final mechanical energy, and subtracting my initial potential energy. Because that's all I have at the beginning. Okay? Do I have formulas that can calculate those two numbers? Okay, so 1/2 mvf squared. The question tells me the person's mass is 72 kilograms and that their speed at the bottom of the cliff is 5 meters per second. So I have m and vf. Okay, and then I have m times g times hi. Well, their mass is still 72 kilograms. G is always 9.81, and the question tells me that the cliff is 25 meters high. So I have all the numbers I need now to perform this calculation. So 1/2 times 72 times 5 squared minus 72 times 9.81 times the initial height, 25 meters. So 0.5 times 72 times 25 minus 72 times 9.81 times 25. Okay, is it okay that I get a negative number? Okay, so I'm standing at the top of a cliff, and when I get to the bottom, I'm still alive and only moving at 5 meters per second. Is that because I have lost energy? Yes. If I kept all my energy, this would be a law of conservation of energy question, and I'd be calculating my death velocity, okay, which would be much higher than 5 meters per second. Okay, it would be much higher than that. Okay, I should have lost energy because that's why the carabiner gets hot. All of that lost energy gets turned into heat and sound as the rope slides through the carabiner, slowing me down on the way down. Okay, so this much work, I think we have 3 significant figures here, so it'd be 1.68 times 10 to the 3 joules. Okay, and that would be negative. I've lost that much energy. Okay, if it's from the point of view of the carabiner, then I mean the carabiner hasn't really gained that much energy. It's gotten hot, but it hasn't gained that much mechanical energy. It's gained that much thermal energy. Okay. All right, everyone kind of follow what we did there. Okay. Still the same as the inclined plane we did yesterday, just much less involved than the inclined plane from yesterday. Okay. I want you guys to try number 2. There's a couple of little things I want you to notice about number 2 in terms of forces and energy. Okay, so I'm going to give you a couple minutes on number 2 here, okay, and see how you do with that one. So there's just something I want to illustrate to you here with question number 2, and it's the relationship between what type of energy the net force changes and what type of energy the rest of the forces change. Okay, if there's a net force, what does the object do? It accelerates. If an object is accelerating, then its velocity and speed are changing, and as a result, its kinetic energy is also changing. Everyone agree with that? Okay, so if there is a net force, kinetic energy will be changing, and it is the net force times the distance that will calculate for you how much that kinetic energy will change. To change the potential energy of an object does not require a net force. I can lift an object as long as I lift it at a constant velocity with no net force. Okay, so I may have a force that's just changing the potential energy of an object, and that's kind of what we're looking at here. Okay, to start out with on number 2, they tell us there's this much force, 150 newtons, acting on a 9 kilogram mass, lifting it to a height of 5 meters. Okay, is work being done? Definitely. Okay. There's definitely a change in potential energy. There could also be a change in kinetic energy. We don't know that yet. Is everyone okay with that so far? Because there's a net force, because there's a force, and they tell us it's being lifted, we know for sure there's a change in mechanical energy going on. If there's a change in mechanical energy going on, then work is being done. And I can calculate that in one of 2 ways. Okay, mechanical energy final minus mechanical energy initial. I can't use that here. Why not? I don't know enough numbers. I don't know the initial height, the final, well I kind of know the final height. It's 5 meters above the initial point. I can make it 0 and 5. Okay, do I know any of the speeds involved? I don't even know if there's a change in speed right now. But I have a force and I have a distance. A height is still a distance. It's just a vertical distance. So I could calculate the work being done just by going force times distance. All right, so that's my first step. Take my 150 newtons and multiply it by the 5 meters, okay, over which this is occurring. So we should have 750, yeah. Okay. All right, 750 joules worth of work are being done by this force. All right. So that's part A. Okay, it's part A, just act. Sorry, I'm getting a weird look for Florence, but where did I lose it?
That's just my face.
No, you were going.
Sorry, I just did it.
Okay. All right, so I've got part A here done. I've calculated the work by going force times distance. Now, part B says, what's the change in gravitational potential energy? All right, well, gravitational potential energy can be calculated this way. M times G times H. Everybody okay with that? The question tells us the object was lifted 5 meters. You generally lift stuff from the ground. okay? Even if we're not lifting it from the ground, we don't really need to know initial and final heights as long as we know the change in height. We can calculate how much work was done to change the potential energy. So all I'm going to do, okay, is take my 9 kilograms worth of mass, multiply it by 9.81, and then by 5. Okay, that'll calculate the change in potential energy that occurred. Okay, so 441.45 joules. Okay, I did 750 joules worth of work. Only 441 of that changed potential energy. So there's still some work left over. Agreed? Okay, if there's still work left over, then this object is not moving at a constant velocity, it is accelerating. Okay? There's no mention of friction or anything here, so I'm not losing that energy to non-conservative forces. It's doing work. Okay? And that means it has to be changing the other kind of energy, which is kinetic. Okay? So I did 750 total joules worth of work. 441 of that is responsible for just lifting. The rest is responsible for accelerating the object. So this object is also accelerating upwards. So part C asks, what's the change in kinetic energy of the mass? How would I calculate that with those two numbers? Just subtract them. Yeah, okay. If I take the total work done and I subtract the amount of work done against or to change the potential energy, that should leave me with the change in kinetic energy that would be left. Okay, so if I do that, so 750 minus my answer. Okay, so 308.55 joules of energy, or of work, sorry, changed the kinetic energy. So sorry, 308. Okay. I wouldn't have asked how much you changed the kinetic energy by. I would have asked how fast is the object going now. How can I calculate that? Nope, not F net equals m times a. I can't use that because I don't know what the acceleration is.
Is it then 1/2 times mass v squared?
Yes, it is. This is my change in kinetic energy. Even though it doesn't outright tell me this thing started at rest, I can assume it did. I lifted it. Okay? Generally, things aren't already moving when you lift them. Okay? So I can say that this 308 is now my final kinetic energy. Started with none. Now I have this much. That equals 1/2 mvf squared. And I could now calculate how fast that object is moving by simply dividing both sides by half of m, and then what? Square rooting. Okay, that'll get me vf and tell me how fast the object is moving now after all of that. So I take that 308, okay, and I would go it's a 9 kilogram mass, right? So I'm just going to divide by 4.5. Okay, so that object is now moving at 8.3 meters per second. Bless you. Okay, that's the kind of places we're headed for. Questions?
For that A bit, why didn't you count the gravity force?
I did. That force is the total force being used to lift the object.
Oh, did they say that in the question?
Sort of. They don't outright say it. It just says the force of this much acts on this mass, lifting it. Okay, so that's all the force upwards that's being used. With me there? So if I was drawing a free body diagram of this, which is probably a way a lot of people started it, okay, I would have 150 newtons up, and I would have force of gravity down, which would be 80. Whoop, 20. So 88.2 nuts. Okay, so actually this is going to be a good point, because how many people did it this way? Drew the free body diagram, did the forces. Okay, remember yesterday I told you that's the slow way? It's going to get you the right answer, I'll show you why. Okay, but it's slow. Okay, so I've just drawn a free body diagram, which it didn't have to do when I solved it. Okay, didn't need it. All right, so I've got 150 up, 88.29 down, 9.81 here. Okay, if I want to calculate the change in potential energy if I want to calculate the work done, okay, in accelerating this mass, I still have to do this step. I've just drawn a free body diagram, which helps. Yes or no? Okay. Then for part B, it says, what's the change in gravitational potential energy? Well, I could take this number here and multiply it by what? Distance, which is 5 meters, which is exactly what I did here. Right? To calculate the 88.29, what did I do? I multiplied 9 by 9.81, and then I multiplied by 5. Did the same calculation. Okay, that's why I get the same answer. Now, for the last part, what's the change in kinetic energy? All right, so this is the part that would take you much longer using this method. Okay, if you're using forces and not energy, okay, then what you're going to do is you're going to find the net force by going 150 minus 88.29. Whoops, not 8.29. 150 minus 88.29. Okay, so there's my net force. Now, if I multiply that by the distance, do I get the same number I got down there? It's 5 meters, right? The net force is what changes the kinetic energy. Remember I told you that? Okay? It's the net force that causes the acceleration, so it's the net force that causes the change in kinetic energy. That's why net force times distance gives me the same number as the change in kinetic energy that I got before. But did I have to do a lot more work? There's way more calculations than just subtracting two numbers. Okay? That's a lot less work. Okay? Subtracting those two numbers. Okay? It gets you the right answer. Okay? Because either way, okay, is using physics to get there. Okay? But using work energy theorem is still going to be short. All right. So we kind of did number 3 in doing that example. That's what number 3 is supposed to illustrate, is that you can do this with forces as well, but it takes you a little bit longer. There's a few more steps. Okay. All right. I want you to write this one down and try it. It's very much like the one we did with the inclined plane yesterday, except this object is being pushed down the ramp. Okay, let's look at the setup of this one at least. Okay, so I've got this ramp. Okay, I know that the ramp is 15 meters long. Okay, and I know that there's a 1,500 kilogram car on it. Okay, and I know that the ramp is 3 meters high, and that the car begins at the top of it, so I should probably draw that better. Okay, so the car starts up here at the top, 1,500 kilograms, 3.0 meters above the ground, right? At the starting point, it's also moving at 1.2 meters per second. Okay, so I know what VI is. I know what my initial height is. Okay, that's what those two numbers are. I also know the mass of the car. Okay. Now, it says that on the way down the ramp, a 450 Newton force is being applied. Would the car go down the ramp on its own? Probably. Okay? I mean, if I just let the car go, it would probably roll down the ramp on its own. But I'm also pushing it, which means I'm doing what? Work. If I just let the car roll down the ramp, and the ramp is frictionless, is any work done? No, then it's just a law of conservation of energy. It's a roller coaster. Okay? I've got my initial height, my initial speed, my final height, my final speed, and I can calculate everything from there because no work is done. But in this case, work is being done. There's a force acting down the ramp. So, since I see that, I immediately go that work is equal to the change in mechanical energy, because it's asking me what's the speed of the car going to be down here at the bottom of the ramp. Well, what's my final height if I'm at the bottom of the ramp? 0. Okay. And I'm looking for my final speed, knowing that I'm also pushing the car and doing some extra work, okay, in addition to what gravity is doing. Okay, so how would I calculate the amount of work that's being done here, since I know the force and I know how long the ramp is? Multiply, right, okay? So I'm going to have that force times distance is my work, and that's going to equal my change in mechanical energy, which we've done a bunch of times before. It's final minus initial. So that's going to mean m times g times h final, okay, plus 1/2 mvf squared. So there's my final mechanical energy, okay, kinetic and potential, okay, minus m times g times hi plus 1/2 mvi squared. Okay, what part of all of that do I not have? Question wants me to find final velocity, speed at the bottom of the ramp. Okay, so I'm looking for this. I'm looking for VF. I know everything else. I know the force, I know the distance, I know the mass, I know initial and final velocity and height, and I know final height. In fact, I can make my life really easy here and eliminate this, right? Because this is 0. All right, so I'm going to write that out again, but I'm going to shorten it, okay, so that I'm looking at this instead. So force times distance equals 1/2 mvf squared, okay, minus m times g times h initial, plus 1/2 mvi squared. All right, I'm trying to get VF by itself. What can I do with this right now? Yeah, add it to the other side. Move it right over right now. Okay, then what I would be saying is the work plus the initial energy equals the final energy. Okay, that's what I'm saying when I do that. Okay, is that mathematically true? Sure it is. All right, so force times distance, my work, plus m times g times h initial plus 1/2 mv initial squared equals 1/2 mv final squared. Okay. All right, I'm trying to get VF by itself. What do I do now? Divide by 1/2 of m and square root. Okay, so this works a lot like the roller coaster questions, but in terms of manipulation. You just have this extra piece of the work being done. Okay. All right, so when I plug in my numbers, okay, I have 450 newtons, that was the force pushing down the ramp, times the distance, the length of the ramp, plus my initial energies. So that will be 1,500 kilograms, the mass of the car, times 9.81, times the initial height, 3 meters, plus my initial kinetic energy, 1/2, times the mass, 1,500, times 1.2, that was the initial speed, squared. Right? And I'm going to square root all of that after I divide it by 1/2 times 1,500. Okay. So the square root of 450 times 15 plus 1,500 times 9.81 times 3 plus 0.5 times 1,500 times 1.2 squared divided by 750, 1/2 of 1,500. Okay, so at the bottom of the ramp, the car will be moving at 8.3 meters per second. Okay, is there another way to do that question? Could I use forces to do it? I could, but if you thought that seemed like a lot of work, okay, believe me, using the forces is more. Okay? If we're using the forces, okay, then we have to draw a free body diagram. We've got to have the 450, we've got to have F parallel, we've got to have, okay, all those other things in there. We've got to do a trig calculation in order to get the angle of the ramp because we don't have that. Okay, all of that other stuff comes into play if I'm using forces in order to do this. Okay, it's much quicker, right, to do this. I know it seemed like a lot of work, but right in the end, it was manipulating one formula. Okay? That was all we had to do, was manipulate one formula. We had all the numbers we needed. Okay? We didn't have to calculate any new numbers using this method. If you use the forces method, you have a lot of new numbers you have to calculate, which increases the chances of making a mistake. Right? That's the other reason it's better to do it this way. Not only is it shorter, but you don't have to rely on as many of your own calculations. All right, questions on how that one works? Okay. That's pretty involved, okay, for a work energy theorem question. They probably wouldn't get much more involved or difficult than that. Okay, so this one is similar. Okay, you've got a large crate rolling along a conveyor. The conveyor uses gravity by being angled at 15 degrees below the horizontal to allow the crates to roll down the rollers. Okay, crates are moving at 0.75 meters per second at the top of the conveyor and accelerate to the bottom, which is 2.5 meters below the top vertically. Okay, there is a frictional force of 150 newtons along the length of the conveyor. Okay, at what speed do the crates leave the conveyor? Right. This one is, I guarantee you, as involved and difficult as a work energy theorem question would get. There are one or two intermediate calculations involved, no matter which way you do it. Okay, so let's just draw it out first, and I'll let you guys have at it. Okay, it's 15 degrees above or 15 degrees below. 15 degrees, no matter which way you look at it. Okay, the crates are starting up here at the top. Okay, they have a mass of 200 kilograms. Okay, when they are at the top, they are 2.5 meters higher than they are at the bottom. Okay, and they are moving at 0.75 meters per second. Okay. There is a force of friction acting up the ramp of 150 newtons. What is that force of friction going to do? It's going to slow it down, which means it's doing work. Okay? That force of friction is doing work, but it's not doing positive work, it's taking energy away. Okay? So the energy at the bottom of the ramp is going to be less than the top of the ramp due to the work done against friction on the way down the ramp. Okay? So I would suggest that one of the things you need is the length of the ramp. You don't have that, and you will need it in order to calculate the work done by friction down the length of the ramp. Okay? It's still going to be this kind of a question. Okay? And you will still have to do force times distance for this. All right, give you some time to work on that. Okay, let's look at one of our intermediate steps that needs to be done in order to get this question finished, and that is I need to know the length of the ramp, because that is the distance over which the force of friction is acting, and I need that in order to calculate the work done using force times distance. Okay, so that first calculation involves me calculating the hypotenuse of the ramp, knowing its opposite side is 2.5 meters and the angle is 15 degrees. Okay, so I'm going to say that the sine of 15 degrees equals the opposite side, 2.5, over the hypotenuse, which is what I'm looking for. Okay, so if I want to find the hypotenuse, I manipulate, okay, bring the hypotenuse over here, and that will be 2.5 divided by the sine of 15 degrees. Okay, so 2.5 divided by the sine of 15. tells me that the ramp is 9.66 meters long. Yeah, obviously you want to keep all those decimals for when you do your work calculation, your force times distance calculation. So that's the first intermediate calculation that you have to do in order to solve that problem. Okay, give you a few more minutes before I do the next one. Okay, so now that I know kind of the situation here, I want to expand out my work as a change in mechanical energy equation here so that it reflects everything that's going on. Okay, so I'm going to have the work done by friction will be the force of friction times the distance or the length of the ramp, and that's going to equal, okay, m times g times hf plus 1/2 mvf squared. Okay, minus my initial energy, so m times g times hi plus 1/2 mvi squared. Are any of those zero? Question says, at what speed do they leave the bottom of the ramp? That means I don't have any potential energy final because the final height is 0. Okay? So I'm looking for VF. Same calculation as in the last question we did. So I'm going to add over my initial energy. I'll have force of friction times distance, the work, plus the initial energy, m times g times h initial plus 1/2 mv initial squared. That's going to give me 1/2 mvf squared. And I want to get VF by itself. So that's going to be divide both sides by 1/2 of m and then square root in order to get VF. Okay, so the same manipulation as we did for the previous question. Okay, we're just going to have a different number in for work here. All right, so we're going to have our force of friction, which was 150 newtons. Okay, so 150 times the 9.65 or whatever it was, I've still got it in the calculator, okay, plus the mass, which is 200 kilograms times 9.81 times 2.5, the initial height of the ramp, plus 1/2 times 200 times 0.75 squared, divided by 1/2 times 200, okay, and that'll get us our final speed coming off the bottom of the ramp. Okay, so we're going to have that 150 times our answer, the length of the ramp with all the decimals, okay, plus 200 times 9.81 times 2.5 meters in height, plus 0.5 times 200 times 0.75 squared, okay, end bracket, divided by 100, that's the bottom. All right, so we're looking at 8 meters per second exactly at the bottom of the ramp, okay, coming off. Okay, tomorrow some more work energy theorem stuff, but more focused. Listening, please. But more focused on just potential and kinetic energy. Okay, we'll be doing a lab Thursday, right, on energy conversions. Okay, simply running a cart down a ramp, similar to what happened here. Okay, but looking for how much friction is involved and all that kind of stuff. And then obviously I put your unit exam date up there the other day, November 9th. Okay, so it's coming up. It was 2 weeks from yesterday, so you might want to start looking things over because work energy theorem and law of conservation of energy are the last two things in this unit. The law of conservation of energy is completely reviewed from Science 10. We add nothing new. Right, so make sure you're looking over all of your stuff here, guys.